Hello everyone, I'm Dr. Shruti Pandey from University of Louisville, and today we are going to talk about inductors, right? So what are inductors? Before starting or before going deep into the inductor, first we'll talk about the Ampere's law because that is the basic foundation of inductor. So if we are taking any conductor, let's say this is a conductor, and we inject an I amount of current in the downward direction, or we inject a current from this side to this side, you will notice that there is a kind of magnetic field across it, here, right? Magnetic field will be there across that conductor where that electric current is circulating, and that you can easily check. Like, take a conductor, inject some amount of current over it, and just take a magnet nearby. Like, if you will take a magnet here, this magnet is going to get attracted if it is in that magnetic range. If it is here, then definitely not. But if the magnet is here, this magnet is going to feel the attraction, right? Because of the magnetic field, because of this magnetic field created by this current I. Okay, so what will happen, and what will be the direction of magnetic field? Like, is it going from inside to outside or outward to inward? So that you can know with the help of Fleming's right hand rule. So like, if right now the current is in downward direction, so this thumb is showing the magnitude, or sorry, the direction of the current, and this, the curl of the other fingers, that is showing the direction of the magnetic field. So this is the downward direction of current, and this is the direction of magnetic field, right? So this is showing that it is going outward from this side and inward from this side, right? So this is a magnetic field. Now if we take this wire, the same conductor, and if we try to make a turn like this, if we try to make a turn like this, and then if we try to give it a power supply, and let's call it as an AC power supply, right? And now if we are giving it a AC power supply or power supply, right, what will happen? The kind of magnetic lines you can feel here, the same kind of magnetic lines you will feel here, right, across each conductor. Like, this is one conductor, this is complete one conductor, so this is conductor, this is conductor, this. Similarly, you are going to feel the magnetic lines across each of these conductor, and this accumulating all these magnetic lines, because of their accumulation you will see these kind of magnetic lines, right? These kind of magnetic lines because of their accumulation. And you will also feel a permanent electromagnet here with this polarity. Let's call it as that this side it is north, this side it is south, when the current was flowing in this direction, right? And now if you try to change the direction of current, that is, if the current is in this direction, you will see that the polarity of that permanent electromagnet also changes. Okay, so yeah, so this is the Ampere's law, right? Direction of magnetic field. So direction of magnetic field is due to Fleming's right hand rule, right? So these are the two basic concepts you should know. Now let's talk about that how this magnetic field is getting how this magnetic field is created and all. So one more thing I would like to tell you here is that I'm sure that you might have heard about a term which is known as flux. If not, then what is this magnetic flux? So whenever I is increased, this I, the supply current, whenever this I supply current is increased, you can see that magnetic field is increased, right? So you will keep on increasing the magnitude of this current, the magnetic field across this electromagnet, or the permanent electromagnet, which I'm saying that it is being created here. So these magnetic lines or magnetic field, the magnitude of this magnetic field can be increased or can be enhanced as we increase the current, and therefore after this a flux is created because of that. What is flux? Flux is nothing but how many or how much magnetic field lines crosses an area, or maybe we can write it in this way, that how much magnetic lines, or how many is probably the appropriate and better word, then how many magnetic lines crosses an area, right, within a respective time, within a particular time. So how many flux lines or how many magnetic lines an electromagnet or an area can accommodate across it, that is what flux is. Okay, so you got to know that we are increasing this current, magnetic field is increasing and flux is increasing. So that way you can get a relation that phi, or the magnetic flux, this is magnetic flux because of those magnetic lines, that how many magnetic lines are passing in through an area. So this is directly proportional to the current, that as we are increasing the current, flux will also increase. So this is one relation. This is also directly, or maybe I'll write this sign, this is also directly proportional to number of turns. So if we'll try to increase the number of turns, right? So if this is like this, there will be, let's say the magnetic flux will be phi 1, right? And now if we are going to increase the number of turns, right, if we are going to increase the number of turns, let's say the flux created is phi 2. So phi 2 will definitely be greater than phi 1, because here the number of turns, because number of turns will be more, so the flux linkage will be more magnetic field lines will be there, right? So the flux linkage will also be more. So that is the reason I'm saying that here number of turns is more, so the flux created here will be more than this one which has less number of turns. Okay, so these are the two relations you got to know. Phi is directly proportional to I and phi is directly proportional to N. So phi directly proportional to I can also be written as phi is equal to L into I, right? Where this L is inductance, or you can say that it is a constant which gives relation between this phi and I, between phi, that is magnetic flux, and I, right? So this is all about this. Now let's move forward. Okay, so I'll get back to that point again, that whenever the current which is passing through this inductive coil, this is a coil, right, a coil stick structure. So whenever a constant current is passing through it, everything is fine, no problem is there. Whenever an alternating current is increased, which is increased from here, I told you that magnetic field lines will increase. Because of that, flux is going to increase, right? Flux will increase, and what will happen because of that? So now comes into picture Faraday's law. What does Faraday's law say? E is equal to minus n d phi by dt. That is, there is a generation of this EMF, that is electromotive force. Okay, so here comes EMF, right? You can see that EMF is directly related to d phi by dt. What is d phi by dt? If the alternating current is changing, like this current is changing or continuously changing with time, right? So if there is di by dt, that is current is changing with respect to time, magnetic field lines are also changing with respect to time, definitely the flux created because of this changing current will be a changing flux. That is, this flux is changing with respect to time. Okay, and whenever there is this changing flux with respect to time, always there is an EMF, and EMF is nothing but it's voltage, right? We know that there is always a higher voltage and a lower voltage, and because of that the current is flowing from higher voltage or higher potential to lower potential. So this is nothing but, and this voltage we also call it as EMF, that is electromotive force. This is that force which is forcing the current to flow from higher potential or higher voltage to lower voltage. Okay, so here comes EMF, and EMF E is equal to minus n d phi by dt. So this d phi by dt is increasing, this E is also increasing. Now one very good thing, so maybe I'll write somewhere here that what is this? This is nothing but Faraday's law, right? Faraday's law of electromagnetic induction, right? So this is Faraday law of electromagnetic induction, and this is E is equal to minus n d phi by dt, where this is change in flux with respect to time, and this is nothing but number of turns. So number of turns will increase, the EMF will also increase, and I told you that EMF is nothing but a voltage, that is electromotive force, okay, which is forcing the current to flow, which will force a current to flow. We'll see next. One thing which is to be noted here is this minus sign. What is this minus sign? This minus sign is nothing but it gives a very beautiful concept, which is Lenz's law. What does this Lenz's law say? Lenz's law say that this EMF or this voltage is going to oppose its own cause. This is what Lenz's law is, that whatever we are trying to generate or wherever this Lenz's law we are applying, that particular quantity is opposing its own cause. So here that quantity is EMF E, and it will oppose or negate its own cause. And what is the cause of this EMF? The cause of this EMF is this current, is this alternating current. This was that current which is increasing. Because of that, magnetic field lines are increasing. Because of that, flux is increasing, d phi by dt is increasing, and therefore EMF is created or EMF is increasing. So this is directly or indirectly created because of this current. So this EMF is going to oppose the current, and this minus sign indicates this. Okay. So one more thing which comes here into picture is that whenever there is certain voltage, always there is a current. So this current was the main current, and now let's call it as I main, right? So I main gave birth to these magnetic lines because of this flux is there, and which gave birth to this EMF, which is a voltage. And whenever there is a voltage, there will be a current, right? And that current we'll call it as a secondary current. Like this is the main current or primary current. There is a secondary current which we will call as induced. Like this is the another current. So when I say that this EMF is going to oppose its own cause, so maybe I'll take a different slide. So when I say that this EMF, or we are calling it a voltage, opposes its own cause, right, which is indicated by this negative sign minus d phi by dt. So that means this E is opposing I main, that is the main current, this I, which is circulating inside this coil. This EMF gives birth to I induced. That is because this current we are not injecting, we are only injecting this I main. This is the current which has been induced by itself, right? And this property, the induction of this current or the introduction of this current in the circuit, this property we also call as self-induction, right? Self-induction, because this current has been this is induced by itself, right? So we can also say that this I induced opposes I main, right? As E opposes this I main current, therefore I induced, which is induced because of this particular EMF, will also oppose the I main current. So I main current, let's say that I main current was flowing in this direction, it is coming like this. So now I induced will oppose this. So this is I induced, and let's say that this is I main current, right? So these are the two different current, and this is also one of the reason that the current, the change in the current or change in current in the inductor, in case of inductor, is not instantaneous. The way we have discussed that capacitor does not allow sudden change in voltage, similarly the inductor does not allow sudden change in current, because there is this thing or there is this thing which is continuously opposing or trying to maintain constant, like the I main current increase from 2 ampere to 4 ampere, there's something which is trying to oppose it and letting this I main to be constant or to sustain constant around 2 ampere, right? So this will keep on opposing and keep on trying to maintain the this primary current or the main current as a constant value. So capacitor does not allow sudden change in voltage. Similarly, inductor does not allow sudden change in current, right? So from here we can conclude that in any application, if we want to maintain a constant voltage anywhere, or if we are in need of getting a regulated and a constant voltage, we can use capacitor there. We will use a charge capacitor there, right? And this charge capacitor will remain charged or will remain or will work as a constant voltage source until we are connecting anything to it, anything in parallel to it, to make or to get it discharged, right? Until that time we are going, or we will get, or we can use the capacitor as a constant voltage source. Similarly, whenever we want to or we try to maintain a constant current, like some application is there which is not demanding the sudden, like 0 ampere 2, then directly 10 ampere, then directly 15 ampere. If we are not looking for any such application and we want a constant current magnitude of 2 ampere or 4 ampere, we will always connect inductor in series to that. So this will be that circuit or load, and from this inductor we will always get a constant amount of current, because this will not allow sudden change in current. Okay, so that way the current, this is time, this is current, so that way the current will slowly increase, right? So that was it. The second thing which comes here into picture is that there are one or two slides here, maybe we'll just go through it. So inductors are basically coil of wire. The coil may be wrapped around an iron or ferrite core. Yeah, so this core also plays a very important role. So the better this core is, the more it will behave like electromagnet, more there will be the amount of current, or better magnetic field will be there, right? Or better flux things will be there, or better inductance will be there. So generally we choose this core very precisely to make the conductivity, or to increase the efficiency of any inductor, right? So this coil may be wrapped around iron or ferrite core to better contain the magnetic flux or increase the inductance of an inductor. Okay, so one thing I would like to again tell you here is that we were discussing this case, that this current we are trying to increase. Let's close that point here first. So I was saying that initially the current is going to increase like this, and at certain point this current will achieve its threshold value, right? So what am I saying with this? That this current here is constant now, right? That means the change in current with respect to time is 0, right? Because even the time in changing, this is 0, and differentiation of any constant value is equal to 0. Okay, so if di by dt is 0, that is change in current with respect to time is 0. Similarly, the flux, because eventually this current gives rise to magnetic field, and that gives rise to phi, and that gives rise to d phi by dt. So if now when the current is constant, then di by dt is 0, magnetic field lines will be 0, and this d phi by dt will also be 0, right? Because there will be no change in flux because of this time. So what happens in this duration, that now whenever we'll stop, or we can also see it in this way, that this constant means that now we have stopped supplying the main source current, right? Now we are just like we are in 0, like right now this magnitude let's suppose that we have kept 0. Okay, so what will happen in this time, that all the magnetic energy here will be stored in form of that magnetic lines, like magnetic lines was there and all the flux and everything was there. So there is lot of energy stored in inductor in form of magnetic energy, right? So I told you that, you remember that there was capacitor and there was a process which was known as charging of a capacitor. So whatever we were doing here is the process of charging or energizing an inductor. So capacitor is charged and discharged, and inductor is energized and de-energized. So in this all process, this capacitor was being energized, and whenever we have cut off the input supply, there is no increase in increment in current, no flux is generated, no EMF because of this flux is there. So in that duration, all the stored energy, now if we like to, like, if the circuit is like this, right? So now when I have I main, it becomes 0. So this inductor is fully energized now, because of that whatever main current was coming and whatever the process was happening, because of that this inductor is de-energized now. And now if we connect a bulb load here, this inductor will get de-energized via this path, right? I'll show you. This path is with green in color, so this will go like this. One more interesting point here is, I'll tell you. So this was the circuit. Let's get back to the capacitor circuit, right? So this was capacitor and this was a bulb load, right? So during charging of capacitor, the current was flowing like this, right? From positive of V supply, this is capacitor, this is load, which is a bulb load, or we can also call it as R load. So the capacitor was getting charged in this direction, and when the capacitor is fully charged, this become positive, this become negative, and now when it wants to discharge, the current direction is opposite, right? So the direction was like this during charging, and the direction is like this during discharging, right? So we got to know that there is always a change in the direction of current in case of capacitor. Why so? Because capacitor does not allow sudden change in voltage, and therefore while discharging it is trying to change its current, right? Similarly, in case of inductor, right? So this was inductor, and let's say that this is a bulb load. So what is happening here is that inductor was charging like or energizing in this manner. So there the polarity was this positive, this negative, and inductor does not allow sudden change in current. So the way capacitor has changed the direction of current immediately, right? The inductor cannot do that. So what will happen? Inductor will have to change its polarity, voltage polarity then. Here current direction can change because voltage cannot, right? So voltage cannot, therefore current direction can change, current can change its direction. Here current cannot change its direction, it resists the change of direction, therefore voltage polarity change, right? So what will happen in this case? In this case the voltage polarity is going to, because current was flowing like this, so across inductor current will always, maybe I'll draw in this with this color. So in case of inductor, the current will always flow like this irrespective of anything, right? So in the discharging case also, where to draw it, let's draw it here. In discharging case also, the current is going to flow in the downward direction. So therefore now the voltage polarity will change, and it will be plus here and minus here, and therefore as the current flows from plus to the negative, so keeping the direction of current constant, right, keeping the direction of current constant, the polarity of the voltage will change. So initially it was plus minus across the inductor, and now the polarity is this side plus and this side minus, and the current direction. So the red one was the current direction when the inductor was charging itself, and the green one is the direction of current when it is discharging. So you can see yourself that the current has not changed its direction, rather voltage polarity has been changed. So that is also one of the very important and important property of inductor and capacitor both. Okay, so so it is, the unit is Henry, like the capacitor unit is Farad, the unit is Henry here. Many inductors have small inductance, so we call it as millihenry, that is 10 raised to the power minus 3. Inductor looks like this, and yeah, so we'll quickly come back to the equations. So just remember, the in case of capacitor, so it was I is equal to C dV by dt. Here it is V is equal to L di by dt, right? Oh, I think so. It was yeah, I think so. I'm correct. I'm correct if I'm not mistaken. Yeah, it was I is equal to C dV by dt. And then here we did integration at both the sides, and it was I by C. We'll write it as this only. So it was 1 by C I dt is equal to V. So this was the current term there, and this came out to be the voltage term there. This is the voltage term here, and again we'll do integration at both the sides. So you can see that integrating both sides, this L comes downside, so it will be 1 by L, then integration of V, and this di by dt is at this side, and it will become it, right, and definitely K. So these were the formulas for capacitor. These two are the formulas for inductor. So you just need to remember these. Here this initial condition has also been taken into consideration, that if somebody says that there is certain amount of current which was flowing before what? Let's say that there is a switch here, right? So before closing the switch or before connecting this inductor to this main supply, there was already some amount of initial current which was flowing across the inductor because of the certain turn on which has been taken place before. Like initially this was closed and then it was turned on, then it was turned off, and then it is turned down again. So because of the previous turn on, there exists certain small amount of current. So if this will be asked in the question, this value will always be given, that 0.2 ampere was the initial current. So this current value will always be given. Okay, so remember these formulas. Then this is the energy stored in inductor. So I did not tell you the energy stored in capacitor. That is important. So energy stored in capacitor is half CV square, and energy stored in inductor is half Li square, right? So these are the two energies. This is for capacitor, this is for inductor. Remember this formula also. Yeah, now the next important thing is, I told you that in case of resistance R1, R2 and R3, similarly capacitance, right, C1, C2 and C3. So when these are connected in series, it will be R1 plus R2 plus R3, and same will be the case in inductors. So you can see that these three are connected in series, so it is directly connected as L1, L2, L3, whereas in case of capacitor, it will be, in case of series, it will be 1 by C1 plus 1 by C2 plus 1 by C3. And in case of in case of parallel, so if resistors are connected in parallel like this, it was 1 upon R equivalent 1 upon R1 plus 1 upon R2 plus 1 upon R3. So resistor, the case is same here. So L and R, they both have similar, exactly same series and parallel formulas, and capacitor one is exactly the opposite. Okay, so these are the important things you need to remember. And this is one last important topic, which is reactance. So I told you that there are three elements. One is R, one is L, one is C. So there is something which is known as resistance. which is the case in in case of resistor, we talk about the property of the resistor to oppose or resist the current flowing across it, right? So this is the current. So the property of this R, which is resisting the flow of current, is known as resistance. In these cases, there's a term which is known as reactance. So this is reactance. Rather, I'll not write X here. And this will be further XL in case of this, known as inductive reactance. And this is XC, known as capacitive reactance. Right, so these are two different reactances here in this case, and I'll tell you one or two more thing. So in case of so it is similar to resistance. In case of like inductance and capacitance, the XC and XL are quite similar thing it is quite similar to resistance. So as resistance is opposing the flow of current, capacitor is trying to oppose the flow of sudden change or the sudden change in voltage. XL is trying to oppose the sudden change in current, and the two has very important two formulas. So it is 2 pi f, or maybe first I'll write that thing, omega L, and this is 1 upon omega C. Omega is an angular frequency, which is 2 pi f. This f is normal frequency L, and this will be 1 upon 2 pi fc. So these are the two formulas again you need to remember regarding reactance, capacitive, inductive reactance and capacitive reactance. So yeah, so we'll quickly conclude all the formulas here, and maybe I need a plain slide here. So in case of capacitance, in case of inductance, so here the what all formulas did we read? E, electric field developed, right, is equal to V by D. D is this distance and this was this V supply, right? Then Q is equal to C into V. The charge stored over the capacitor is equal to capacitance into voltage. Then W is equal to half CV square, right? From here maybe we can write this is phi. Flux is directly proportional to number of turns. Flux is equal to Li. Then here W is half Li square. Next is next maybe we can write these formulas. I is equal to, or V is equal to L di by dt, and I is equal to 1 upon L V dt. If I'm not wrong, let's cross check with this. Yeah, so I is equal to 1 upon L V dt, right? So this we are right. In case this here it is exactly opposite. I is equal to C dV by dt, right? And here V is equals to 1 by C I dt, right? So these formulas, yeah, one more thing, XC is equal to 1 upon 2 pi FC, or we can write it as 1 upon omega C. Here XL is equal to 2 pi FL, or this term is omega L. So for now I can remember these formula. Let's check that is there anything which is missing. Yeah, these things are missing. So I think there is no other formula left. Okay, so in case of capacitor, we'll write here, in case of capacitor in series, we do 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 if there are 3. In case of series, we do just like resistors, L1 plus L2 plus L3 if there are 3 connected in. And in case of parallel, C equivalent is equal to C1 plus C2 plus C3 opposite. And in case of parallel, we do 1 upon L equivalent is equal to 1 upon L1 plus 1 upon L2 plus 1 upon L3, right? So these are the formulas I could think of for right now. So thank you.